Hello everyone. In the previous class we have discussed about the switching cycle and the continuation of that one, that is specifications for switching transistors. So the figure shows the collector current during switching transients, that is going to including the delay time required for charging the junction capacitance and definitions of rise time and fall time. So here the terms TD, TR and TF are shown here. TD is the delay time while junction capacitance is charging, and TR is the rise time, that is from point 1 of collector current to 0.9 of collector current, and TF is the fall time, that is from 0.9 of the collector current to 0.1 of the collector current. So all those are indicated in the graph, collector current IC versus the time. Here the charging time of the emitter junction capacitance needs to be considered here. The charging time of the emitter junction capacitance will be considered going from cutoff to saturation. So we know that what is cutoff region and what is saturation region. So here consider cutoff to saturation. Since the emitter junction is reverse biased in cutoff, it is necessary for emitter space layer to be charged to the forward bias condition before collector current can flow. So therefore we must include a delay time TD as shown in the figure. From this to consider this effect. So the typical values of the TD are shown in the figure. So in the given specification of the most switching transistors along with the rise time TR, so which is defined as the time required for the collector current to rise from 10 to 90% of its final value. So you can observe the figure, the collector current is shown 0.1 IC to the 0.9 IC. So that is denoted as TR. So TR is nothing but the rise time. So rise time is nothing but, it is defined as the time required for the collector current to rise from 10% to 90% of its final value. There is one more, TF, that is fall time, is also defined here. It is shown from 0.9 IC to 0.1 IC. So that is 90% of the collector current to the 10% of the collector current. So this is the third specification. The first one is the delay time while junction capacitance is charging, TD. So that is shown in the figure, TD. Then TR is the rise time, 0.1 to 0.9 of IC, that is 10% to 90% of IC. Then the third specification is the fall time. So that is fall time is denoted as TF, which is nothing but which is required for the collector current IC to fall through 0.9 of IC or 90% of IC to the 10% of the collector current, which is similar fraction of its turn off excursion. Next topic, other important effects. The first one is the drift in the base region, second one is base narrowing, and the third one is the avalanche breakdown. So here in this topic we are going to look into the effects of the non-uniform doping in the base region of the transistor. So here already we have made some assumptions here for the particular device, that is transistor, and we'll consider few small derivations here in this section. So here already we have discussed some modifications, but these are called as the secondary effects. So secondary effects, even though they are the secondary effects, these are not going to be unimportant. These are also considered for a device geometry and a circuit application. So in particular, we are going to find the graded doping, which can lead to a drift component of a charge transport across the base, adding to the diffusion of carriers from emitter to collector. So we are going to discuss the effect of a large reverse bias on the collector junction in terms of widening the space charge region about the junction and avalanche multiplication. We are also going to see that transistor parameters are affected at high current levels by the degree of injection and by heating effects. So here several structural effects that are important in particular device, such as asymmetry in the areas of the emitter and collector junctions, series resistance between the base contact and the active part of the base region, and non-uniformity of injection of the emitter junction. So all these effects are important in understanding the operation of a transistor, and also proper consideration of their interaction can contribute very effectively to the usefulness of the practical transistor circuits. So we will see the first one today, that is drift in the base region. Here there are two figures. The figure shows the graded doping in the base region of a PNP transistor. So figure A, typical doping profile on a semilog plot. This graph is drawn on a semilog graph paper. And the second one is the approximate exponential distribution of the net donor concentration in the base region on a linear plot. So as shown in this figure, there is a sharp discontinuity in the doping profile. When donor concentration in the base region becomes smaller than the constant p-type background doping in the collector. As you can observe from the figure, there is a very fairly sharp discontinuity in the doping profile. So similarly, the emitter is assumed to be heavily doped, P plus. So that you can see from the figure, the two junctions and three terminals. Emitter is heavily doped, so that's why it is indicated as P plus. So heavily doped shallow region, providing a second rather than sharp boundary for the base. Within the base region itself, however, the net doping concentration, so the net doping concentration is N, that is nothing but Nd minus Na is approximately equal to N, that is indicated there, varies along a profile which decreases from the emitter edge to the collector edge. So that is doping concentration. But we can clearly see that the effect of an impurity gradient by assuming for the simplicity that N of Xn varies exponentially within the base region, that is figure B. Observe the figure B. The effect of an impurity gradient by assuming for simplicity that N of Xn varies exponentially within the base region. So the second figure shows approximate exponential distribution of the net donor concentration in the base region on a linear plot. So here one important result of the graded base region is that a built-in electric field exists from emitter to collector, that is for a PNP transistor, thereby adding a drift component to the transport of the holes across the base. So we can demonstrate this effect very simply by considering the required balance of drift and diffusion in the base at equilibrium. So we can demonstrate and see the effect. If the net donor doping of the base is large enough to allow the usual approximation, n of xn is equal to small n of xn is equal to capital N of xn. That is the balance of electron drift and diffusion current at equilibrium. So if the net donor doping of the base is large enough to allow the usual approximation, n of xn is equal to n of xn. The balance of electron drift and diffusion current at equilibrium requires In of xn is equal to q a mu n n of xn epsilon of xn plus q a dn into dn of xn by dxn is equal to 0. Therefore, the built-in electric field is epsilon xn is equal to minus dn by mu n into 1 upon n of xn into dn of xn by dxn. So that is equal to minus kt by q 1 upon n of xn into dn of xn by dxn. So for a doping profile n of xn that decreases in the positive x direction, this field is positive, directed from emitter to collector. For the example of an exponential doping profile, the electric field epsilon of xn turns out to be constant without the electric field epsilon xn turns out to be constant with position in the base. So we can represent an exponential distribution as, that is shown here, n of xn equal to n of 0 into e to the power minus a xn divided by wb, where a equal to ln of n of 0 divided by n of wb. So taking the derivative of this distribution and substituting in the equation of electric field, we obtain the constant field epsilon xn equal to kt by q into a by wb. So since the field aids the transport of holes across the base region from emitter to collector, the transit time Tt is reduced below that of a comparable uniform base transistor. So similarly, electron transport in an NPN is aided by built-in field in the base. So this is about the NPN. So remaining two effects, that is base narrowing and avalanche breakdown, that we are going to discuss it in the next class. Thank you for watching the video.